Welcome to our NPTEL courses on the DC microgrid and the control system. Today we are going to discuss this dynamics of the DC microgrid and its modeling. We were continuing with the grid side modeling. Now we shall now take it out the dynamics of the DC bus for single phase grid connected inverter. Most of the thing it is placed in our domestic appliances. So, what happened? This is the grid side voltage, that is a maximum voltage V max, and ultimately the power is your this is the average power and this is the double of the power. And I am coming to you why it is so, because of this, why it is that oscillations is there. So, here you can see that this blue one is the inverter power and this is the average power, and also inverter power can be positive negative for the time being, and thus what happen, this is the DC power. So, there will be a ripple in the DC power. So, in the steady state, the DC power injection is considered as a constant value PDC as shown in the figure 1. So, this is the red line. The average value of the extracted power P inverter should be equivalent to the PDC, that is what the scenario. So, that the DC bus voltage can be maintained at a steady state value as shown in VDC. But what happened for the reference of the so for the reference of the grid voltage, that is V grid, and it is plotted 1 and it is showing that whole cycle of 0 to 2 pi, where grid voltage is essentially V max or V magnitude into sin omega t, where omega b represents the grid frequency which is in radian per second. Since the unity power factor is considered, that is the operation we will consider here, that grid injection current is expressed as a pure sinusoid without any harmonics. So, I grid equal to I m g sin omega t by P n v P d c minus P d c minus P d c cos of double frequency oscillations, which we have seen there. So, what happened, that is the instead there will be a DC value above with there will be a oscillatory value, because if you multiply essentially 2 sine, you will get essentially sin square omega t, you can split 1 minus 2 cos omega t by 2. So, essentially what one part is your DC, another part is your double frequency oscillation, and that double frequency oscillation over a period of the time of the 2 cycle, over the period of the time of this 1 cycle, it is 0, since it is double frequency. But instantaneously there will be a DC component above it, that is what I have shown in the figure number 1, above it there will be a oscillation of the double frequency power, and thus the DC capacitor CDC provides an energy buffer to accommodate the instant difference between the. So, that is the cause of the INV and this difference between the PDC and INV as expressed in this next equation 4 in the and it can be shown in the figure 1. You can refer back to the slide number 1 by dragging. So, PCDC, that is a capacitor power, essentially it has a PDC that has been fed by this DC to DC converter minus P and B essentially will have a double frequency oscillations, and sometime it will be positive, sometime it will be negative. So, this has to be supplied or by this capacitor. When the instantaneous power P and V, that is higher than the PDC, that this deficit is compensated by the capacitor energy. So, ultimately capacitor will discharge and that will feed that extra power in the period. So, please refer back to the figure number 1, I cannot refer back every instant. So, from pi by 4 to 3 pi by 4, which is highlighted in figure 1. I just show for one reference, please capture it. So, this is the point has been marked here as a blue line. So, you got a P and V more than the PDC. The voltage of this VDC drops from the peak value high to the minimum low to compensate the deficit by supplying the stored energy of the DC bus. So, we require to compensate the designs, or we require a compensator. Essentially capacitor is a compensator, and thus, so half CV square essentially these equations. So, half C in V I square high minus V I square low is the difference between the variation of the input of the capacitor of this before this grid side converter, and that can be minus pi by 4 by 3 pi by 4 PDC dt. Similarly, half C in V square minus V low square is given by the same value pi by 4 to 3 pi by 4, and thus you can multiply this capacitor and this voltage. Essentially these two voltages will give you that power by time, that will be PDC by omega, and it will be essentially PDC, that is the rate of change of power that will be fed from the system. So, we have to take different kind of conditions, that is dynamics of the DC bus for the single phase interconnections. We are in a same thing definitely when peak to peak voltage ripple VDC is specified for the steady state, that you should have this much of the DC link voltage, and the DC bus capacitor CDC can be rated for the single phase gate connections, and ultimately this will be given by this. So, CDC PDC omega VDC into del IDC. So, mind it. So, if you are using one solar inverter which has been designed for the 60 hertz, and if you wish to design in 50 hertz, then we require to change the value of the capacitor, otherwise what you will find that this the ripple will be more. In the two stage conversion system, the DC bus voltage ripple has an indirect influence for deriving the MPPT, because it will naturally change the MPPT point, these oscillations, and thus your tracker unnecessarily has to run and track that MPPT point, and ultimately it cannot, it is changing so fast, may not able to converge. And it is a line frequency. So, for this reason it is 100 hertz for the 50 hertz system. However, the double frequency ripple in the voltage also induces a series harmonics at that point of common coupling of the gate side, that is quite dangerous. It is an even harmonic, you know that even harmonic is generally not there because of the symmetry of the Fourier series, and this double frequency oscillation will inject the double frequency power at a point of common coupling. So, that is what happens. The dynamic. So, what we have shown in the figure 1, the peaks of the INV is at 2 PDC, which you can refer back to the figure, and can be approximated by the multiplication of the IMG into VMG, because if you are feeding a resistive load, then that kind of conditions comes. So, once you have a voltage peak, current is also the peak, and thus you are taking huge amount of current and the power from this capacitor. When the DC to AC conversion, of course, you have neglected the losses of the converter. The values of IMG or the maximum or the VMG are the constant in the steady state, representing the amplitude of the grid current I grid and the grid voltage V grid respectively. Therefore, the value IMG is estimated by the equations I shall show later, which can be utilized as a reference for the grid regulation. This equation will be 9. So, IMG equal to essentially 2 PDC by VMG. So, the dynamics of this DC bus for the 3 phase grid interconnections, we can see another few interesting aspects. For the 3 phase, there will be few things more. When all the 3 phases are balanced, hopefully, and operate at a unity power factor, the power system forms a constant DC value. So, that is one of the important features. Since it shows no variation between the DC power and the accumulations of the AC power, the DC bus capacitor is not rated at the same as the single phase case, which focuses mainly on the double frequency ripple. That is something quite important in case of the 3 phase system. And so, you have the DC bus capacitor is not rated as in case of the single phase case, and which is only focuses on the double frequency oscillations. And thus what happen, the value of the, since you have a ripple of like this will be a 6 pulse converter instead of the double frequency, it will, the frequency will be 6 harmonics. It is 300 hertz or the 360 hertz depending on the your system, and thus the size of the capacitor will be reduced. The volume of the DC bus capacitor therefore is, their capacitor is therefore sized by the filtering effect of the high frequency switching and unexpected power variation. So, thus using a 3 phase system inherently has an advantage over the single phase system, but depends whether you are connected to your PV, whether your power evacuation is done by the single phase or 3 phase, that depends on the rating. So, generally up to 5 kVA we generally allow single phase, above that we allow the 3 phase. So, in case of the 2 stage conversion system, the both the PV side converter and the grid side converter we can consider for the sizing the capacitor. So, we require to design this capacitor value quite well, otherwise there might be a drop of the voltages and all those things. The DC bus energy buffer is designed according to the dominant ripple component. So, that is also we require to keep in mind whether if it is a 3 phase, so it will be a 6th harmonic, if it is a single phase, it will be the 2nd harmonic. And for example, most power electronics converter are switched at a frequency higher than 1 kilohertz. So, the need of the filtering capacitor is less than for the single phase grid connections. So, that is the attribution you can make it. So, let us go for the design of this capacitor bus for the 3 phase system. For PV power system, the power mismatch between DC and the AC stages can be estimated as del P max and del TR, which represents the power difference and the time period of the variation. So, that is something we require to keep in mind. So, where it is match, where it is mismatch. Therefore, since it is 6 pulse, it won't be something like 90 degree. So, we require to calculate, and that time we will say that where there is a mismatch occur, it is TR. So, therefore, the DC bus capacitance can be sized as shown in the this is equation. So, that is the power maximum, that is I max into V max, or the I magnitude into V magnitude into TRR for the duration where the power maximum has occurred, and the 2 VDC into the ripple voltage of this VDC. So, lesser the capacitor value, lower will be the ripple in that way, or you can predefine that ripple is 2%, 5%, accordingly you calculate the value of the capacitor. So, CDC equal to the P max into del TR 2 DC into del VDC plus del V square DC by 2, where DC and del DC are the nominal voltages of the DC bus and the specified ripple voltage. The battery buffer is an important component in DC microgrid in a standalone system, because most of the cases you may have a mismatch between the generation peak and the demand peak, and also instantaneous mismatch between the power between the two entities. Balancing the difference between these two generations and the load demand, and thus what happen, the battery power interface should be able to regulate the DC voltage in a microgrid through regulated power, either injecting or extracting the power from the DC bus. So, once you have a mismatch between the power, so it will that extra power should come from the battery. Once you have a surplus, that power should go back to the battery, and over a period of time, and also the double frequency case. And thus what happens, the DC bus can be modeled as a capacitor CDC in parallel with an equivalent load resistor RL. That is the way we can model it for the microgrid application. Now, this is an active 12 bridge converter. We can have a bidirectional flow of power if required. If it is a resistive, definitely it cannot send back the power, but if it is some kind of regenerative or some other features, then it can be a bidirectional. So, the dual active bridge converter is used for the power interface. The system circuit is shown in the figure 2. This is figure 2. the inductance L here is not considered for the dynamic modeling, because it is a leakage inductance. In a sense, it forms an independent impedance effect and interacts with the high frequency switching. So, we shall neglect it, but in actual model we require to consider it while designing the control aspect of this topology, because mostly it is a lump parameter, it is a leakage inductance of this high frequency transformer. So, this is a bidirectional bridge configuration, and you will be sending power from the battery to this load. And what happened there? The dynamics of the DC bus voltage is dominated by this RC circuit, that is including this CDC and RL, and this can be represented by CDC dVdt equal to IDC minus I0, and which can be further derived into CDC dVdt equal to P battery by DC minus DC by RL, where VDC is the voltage variable and DC represents the steady state value. And from there what we can say is that the power flow equation at the steady state. So, the whatever the power is flowing from the battery is battery voltage plus output voltage into psi pi minus psi into 2 omega ln, where this omega is not a frequency of the grid. So, it is quite fast, that is the frequency of the switching frequency of the converter. That depends, if it is a IGT based system, the switching frequency can be 10 to 5 kilohertz, and phi is a phase shift between this unit in radians, and thus what we can compute from this 13 and 14. So, dVdt equal to battery voltage into psi into pi minus psi omega ln DC minus there will be a regulator factor VDC RL into CDC, where we assume that this battery voltage almost remains constant. So, there is no variation in the battery voltage. So, where battery voltage is the steady state value of the battery, then only this analysis is more fruitful. So, thus what happened, the linearized model of this DC to DC converter can be written in a form of the, we will ultimately form the state space. So, del dVdt equal to battery by 2 omega omega L pi n, where n is the number of turns ratio 1:n we have considered, into CDC 1 minus 2 psi minus phi into psi minus this thing. This psi delta and VDC delta essentially the variation of the phase and the variation of the DC bus voltage respectively, and the model is based on the steady state condition, which is determined by the phase shift phi and the battery voltage V battery, and thus we can have a transfer function like this. So, that is V delta DC by tau is RL battery omega ln omega L pi n by RL CDC into S is a Laplace domain plus 1. So, this will be the overall expressions of it, and thus you can see that it is a first order system, unlike the second order system which we have seen in the previous case. So, from this observation we can say that the parameter, this capacitor voltage, this inductor which mainly we have neglected, the trans ratio and the switching frequency are determined for the designing stage of this dual converter. So, they are considered to be the constant during the system operation. So, we will have a constant frequency operation. So, we cannot use hysteresis controller, and current is increasing decreasing always in the inductor, and thus this is the current through the inductor, this is the always you will find, and that L equal to N phi by I. So, once current is increasing, but you may close to the saturation, thus your value of the phi may not be changing, thus you have a rollover effect. So, value of this inductor will change according to the current, but that effect has been neglected, and while considering that operation we take the nominal value of the inductor. So, actual operations we have to take care of all those things, and they are considered to be the constant during the operations. The system dynamics is mainly changed by the variation of the psi and the RL. So, that is what we want to see, and the small signal model is based on the steady state values for the operating condition, and thus we can see that this converters DC converter works fine if you properly design these entities, that is CDC, L, N and the switching frequency. I have just 2-3 points to take away here in design aspect of here. So, ultimately if you wish to design, how you decide the switches, that depends on the power handling capability of this DC to DC converter. If this converter is IGBT, then it can handle the power up to the 100 kilowatt, and of course, switching frequency required to be lower, and thus it is and ultimately you may be parallelly operating also few converter, that also required to take into the account, and ultimately while designing this, battery will give you the intermittent extra power required from the solar or this thing. So, whatever solar is taken, and if it is a DC, then there is no problem, you can instantaneously fit this value. But if it is AC, solar and battery feeding a microgrid, and there will be a instantaneous variation of the double frequency, and maybe that current fed from this battery instead of the load, and thus bidirectional flow is possible, and also maybe that this capacitor itself can handle that power and can send back the power, then there will be a ripple in the capacitor. And otherwise, if it is feeding a DC system, so battery plus the grid will feed you the required load. Thank you for your attention. I shall continue with the modeling in the next class also.